So let's go ahead and get started. This is the second review for Math 2417. So we'll start off with just a brief little agenda. Today we're going over, or I have plans to go over sections 1.4 through 2 in the textbook. And that covers continuity. You know what? What I'm gonna do. I'm actually just going to type this out. It's a lot easier that way. And what we're going to be covering is continuity, x, derivative, lines, and lastly, some basic differentiation. And if you guys would like to go over anything else, just say something and we'll try and get it done, all right? So, without further ado, let's go ahead and talk about continuity. So what do you guys know about continuity right now? Like, thus far, what's your impression of continuity? Anyone? All right. I guess we'll just go ahead and dive into the definition then. You got someone saying where f of x exists. That's part of continuity, but not all of continuity, right? Because we can have a function that's defined, if we just drew out a quick example. We can draw a function, say, like this, and it'll be defined for the whole set of real numbers. So f of x is technically defined at this point where there's a jump discontinuity. So we need a little more to define what continuity is. So to do that, let's actually go ahead and go over a quick definition of continuity. And to do that, we're going to use limits. So the definition of continuity is specifically where you have limit as x approaches c from the negative side, f of x equals limit as x approaches c from the positive side of f of x, of course, which equals f of c. Or in other words, the limit as you approach a point is equal to the exact value of the function at the point. And that is the definition of a derivative, of continuity. A function is continuous if the limit as a function approaches the point is the same as the function's value at that point. So for instance, if we went ahead and drew out a quick graph, we had something just like this where we've got a whole point and it just keeps going on like that. We can see that our actual function value, if let's say this is 2 and this is 1 right here, then f of, let's just say that's -1, and f of -1 is equal to 2 itself. However, the limit as x approaches -1 is equal to +1. And since these two values are not equal, we say that the function is discontinuous. That is the definition of continuity. If we wanted to go ahead and get into a couple of examples, what we would do is we would just say, for instance, if we have x equals the square root of x. This is a pretty simple example. We want to know, is f continuous at 0? And if we were to actually consider this, we could say, well, f of 0 is of course equal to 0. But we also need to show that the limit of f of x as x approaches 0 is 0. So what is the limit as x approaches 0 of f of x? Um, 0 is actually a bit of a trick question, because if we actually look out and sketch out the function, we can actually see that from the right-hand side, the function does approach 0, but from the left-hand side, the function doesn't exist. So because the limit from the left side isn't the same as the limit from the right side, the limit actually does not exist. So because these two values aren't actually the same, this function is actually not continuous at x equals 0. You can see that that's where it stops. The function itself exists, it's just not continuous. Does that make sense? All right. Good. So, let's see. Yes, with the hand raised, what's your question? Is there like, as in, can you ask questions through the microphone? There should be. If you look at the bottom part of your screen, there should be a little icon that looks like a microphone. So if you click that, you should be able to unmute yourself. Can't find it? All right. That's correct. If the limit does not exist, the function is really not continuous. Having a limit that exists is a condition required for continuity. Good question. So, have you guys discussed one-sided limits in class yet? Yes, all right. Good. I kind of glossed over that. But they're fairly simple, just take the limit looking from just one side instead of both sides. In that case, we'll actually go ahead and move to a couple of practice problems for you guys to do. And your job is just to determine where these functions are discontinuous, if they're discontinuous at all, and then explain why they're discontinuous. All right, go ahead and try those out. I'll give you a couple of minutes to think on those. Right. B is continuous because they both equal each other. Um, B is continuous, and when you say both of them, I'm assuming you mean the function value and the limit as x approaches -2. All right, correct. So what if this -4 had instead been something like a 6? It would not have been continuous, correct. Okay. So one thing that we actually learned from from continuity is there is something called the intermediate value theorem. And what this is it basically says that if you have a function, some function f of x, and it is continuous on some interval from a to b, then you know that for every value k, it's between the value of f of a and f of b, there has to be some point on this interval from a to b so that f of c is equal to k. And really all that's saying is it's a complicated way of basically saying if you have some kind of function and it's like this, and you've got some interval from a up to b, all the way over here, then basically you have some kind of lower bound, some kind of upper bound. So the function really, it just has to hit every y value somewhere between this x value here and this x value here. And it's pretty logical if you think about it. If you can't jump, then there's no way you're going to skip any y values. But it's a really easy way to show that things like zeros exist. So if you wanted to say, for example, you have the function f of x equals the square root of x plus 7 minus 5, and you want to show that f of x is equal to 0 somewhere between 0 and 5. Well, in order to show this, really all you have to do is you can say, I know that f of 0 is equal to the square root of 7 minus 5, and this is going to be, well, the square root of 7 is less than 3, so 3 minus 5 is going to be smaller than 0, so we'll say it's about equal to negative 2, and then f of 5 is equal to, let's see, I've read my example wrong. That should be x squared plus 7, in which case f of 0 is still about equal to negative. But then f of 5 is going to be the square root of 32 minus 5, which is the square root of 32 is between 5 and 6. So we'll say that this is about equal to 0.5. And then because this negative 2 is smaller than 0, which is in turn less than 0.5, we can say f of 0 is less than some value k, or some point at c, which is in turn less than 0.5. So then by the intermediate value theorem, we have to have some kind of 0 on this interval. Does that make sense? All right. So I'll go ahead and give you a, actually, do you guys want a practice problem on this, or do you think you're good? You want a problem? All right. In that case, I've got a problem. Here we go. The problem is f of x is equivalent to x cubed minus 4x squared plus 1. And your job is to show that f of x is equal to 10 somewhere on the interval from 1 to 5. So why don't you go ahead and work through that? And I'll give you a couple of minutes for that. And just go ahead and say something in the chat once you're ready. All right. So in this case, did you manage to show that there was a value such that f of x was equal to 10? No? All right, that's okay. Basically, the main strategy for solving problems like these is you don't actually have to find a specific x. Really, you just have to use the intermediate value theorem. And the easiest way to do that is to say, well, what is the left limit? What is this f of 1 equal to? And in our case, it would be 1 cubed, just 1, minus 4 times 1, plus 1. So that is negative 2. And then we would have f of 5, which is going to be our right limit, which is going to be 5 cubed, 125, minus 4 times 25, so minus 100, plus 1, which is equal to 26. So then, because negative 2 is smaller than 10, which is in turn smaller than 26, by the intermediate value theorem, or the IVT, we have to have some x in 0, 5 so that, sorry about this, so that f of x is equal to 10. Does that make sense? All right, glad to hear it. Due to time, we're actually going to move on now, just so we can make it through everything. So next up, we'll go ahead and move to infinite limits. And really all these infinite limits are basically limits that go to infinity. So you can think of functions like 1 over x, which looks like this. You can see the limit as x approaches 0 from the positive side, 1 over x is actually going to be positive infinity, because you see as x goes to 0, we're going to have 1 divided by something that's smaller and smaller. So our actual value is going to be getting bigger and bigger, as you can see on this graph right here. If you want the formal definition, basically what it is a limit as x approaches c of some value, some function f of x is equal to infinity if for every number bigger than 0 you pick, you can essentially pick an m so for every number bigger than 0, f of x plus delta, I said that a bit wrong, so I'm going to back it up just a bit. Give me just 1 second. So the limit as x goes to some value c of f of x is equal to infinity if for every number m you pick, and m is just going to be some large number, so you can think of it as being just a very large number. If for every m you pick, you can find some kind of delta that's bigger than 0, so that f of x plus delta is going to be bigger than m. And what that means essentially is the bigger the number you choose, the closer and closer you get to this actual value of x, where you're trying to test the limit is. As m gets bigger, you just get closer and closer to that actual value, but you just keep increasing your function value. So for instance, if we just took this 1 over x, and we wanted to say, well, I'm picking an m equal to 1,000. So I want to show that there's a delta so that I can get 1 over x to be bigger than 1,000. So you have 1 over x. Since we're evaluating it at x equals 0, say, so we have 1 divided by 0 plus delta is bigger than 1,000. So 1 is bigger than 1,000 times delta, which means that our delta has to be bigger, sorry, our delta would have to be smaller than just by dividing both sides by 1,000, 1 over 1,000. So for instance, if we plugged in for our delta 1 over 10,000, then we would have 1 over 1 over 10,000, which is of course equal to 10,000, which is bigger than our m, which is 1. That's kind of the premise behind these infinite limits. Basically, you just, for every real number, you can always get closer and closer to that asymptote so that your function value is going to be bigger than that number you chose. If that makes sense at all. Does that kind of make sense to you guys? Yep. All right, cool. In that case, we'll actually just do a couple of really brief examples or practice problems. So a lot of the time, you don't actually have to use that formal definition of an infinite limit. In fact, I'd be pretty surprised if you have to use it at all in your course. Most of the time, it's plenty to just be able to identify where these infinite limits are. So, first off, why don't you identify all the infinite limits of 1 over cosine of x plus 1. Then, what is the limit as x approaches 0 from the positive side of x squared plus 1 over x? All right, and just go ahead and tell me when you're done with those. All right, thoughts, anyone? For, sorry, which one? Oh, is A negative infinity? I'm just trying to, it is actually not negative infinity. We'll go over A in a sec. I think that one's maybe tripping you guys up a little more. Has anyone looked at B yet? B is positive infinity. Good job. Um, so let's actually go ahead and take a look at A, because I feel like this one was maybe tripping you guys up a bit more. B is positive infinity because, of course, this x squared term is going to go to 0, but then this 1 over x term, you can think of as being divided by a smaller and smaller positive number because we're approaching from the positive side, so it's going to get bigger and bigger and go to infinity. So go ahead and actually clear that so we've got a little more space to write with this over cosine of x plus 1. So a big thing to actually look for with these infinite limits or limits that go to infinity is asymptotes. So things like dividing by 0, those will often get you an infinite limit. So in this case, we want to actually look for where this cosine x plus 1 is actually equal to 0. So where is cosine of x plus 1 equal to 0? At pi. All right, good job. So we're going to say when x is equal to pi. And of course, since cosine does repeat, we're actually going to have an infinite number of places where cosine of x plus 1 is equal to 0, right? Every 2 pi times. Every other time around the unit circle, we're going to hit that cosine of x being negative 1. So to represent that, we're just going to say where x is equal to pi plus 2 times some constant k. Goodness, I cannot write a k. So when x is equal to pi plus pi k. Okay, so will this approach positive infinity or negative infinity? That's a question as well. What do you guys think? Positive? Okay, good. Why? Is see, we're never approaching from greater than negative 1, right? So because this cosine of x, it's always going to be bigger than or equal to negative 1, that means that our cosine of x plus 1 is always bigger than or equal to 0, which means we're always going to be dealing with these positive numbers. So if we actually went ahead and graphed this, just a sec, see if I can put up a graph. Then we had a graph y is equal to 1 divided by cosine x plus 1, we would actually go ahead and see how we do have this recurring vertical asymptote limit to infinity behavior going on at about every 2 pi. Make sense? All right. Again, we're actually going to go ahead and move on just so we can get through all the material. So we're going to go ahead and start looking at some derivatives. So if you'll give me just a second, I need to change to sharing screen here. And what we have here is just a little example that I've pulled up. And the big thing to remember with derivatives is a derivative is basically just the slope of a function. So it's the slope of a function, but at only one point. If you can remember our original slope formula, it takes 2 points, like I've got here, points A and point B. And the slope is just going to be rise over the run. So the y value of b minus the y value of a divided by the x value of b over the x value of a. But the derivative is essentially what happens when we take these 2 points and move them infinitely close to each other. So I've actually made a little animation. Hopefully you guys can see this. And you can see as these 2 points get closer and closer together, you get closer to something that's called a tangent line. And that is going to be the slope at exactly 1 point. And it's called a tangent because it only crosses our function at that 1 point. So the tangent line at A wouldn't actually cut through this parabola like you can see all these other lines going through. It would just kind of hit it only at point A. And in order to do this, we have to use a limit. And that limit is going to be, let's see, I want to switch over to airing something else. See, I don't think you guys can see anything. Give me just a sec. And we're going to switch to something a little more low budget, just because Wright's a little better on this. So if we wanted to look at the actual limit definition of a derivative, it's going to be the limit as sum delta x goes to 0 of f of x plus delta x minus f of x over delta x. And in this, you can actually kind of see our old slope formula, where if we have 2 points, one is going to be x comma f of x. The other point is going to be x plus delta x, f of x plus delta x. And what you can see here, here's our first y value. We would have f of x plus delta x minus our second y value, f of x, and you can see this is exactly the numerator we have up here. Then we would be dividing by our second x value, so x plus delta x, take away the first, minus x, and these x's would just cancel. And that actually gives us this definition of a derivative right up here, if we let our delta x go to 0, let the distance between these 2 points be 0. So if you wanted to actually evaluate these limits, just a moment. Then, for example, let's say we wanted to find the definition of we wanted to find the derivative, of f of x is equal to x squared minus 3x. Well, we know that our definition states limit as delta x goes to 0, f of x plus delta x minus f of x over delta x. So f of x plus delta x is simply going to be x plus delta x squared minus 3 times x plus delta x, where instead of just having x, we replace all of our x's with x plus delta x's. Then we would take away our original f of x, so minus x squared minus 3x. Again, this all needs to be in parentheses. We will need to distribute this negative over to this negative 3x. That's a common mistake, so make sure you look out for it. And then that's all going to be over delta x. And of course, we need our limit statement. The limit as delta x goes to 0. So then, if we went ahead and distributed, x plus delta x squared is going to be x squared plus squared minus 3x minus 3 delta x minus x squared minus 3x plus 3x, all over that delta x. And you'll notice all of our terms without a delta x should cancel. We have this negative 3x right here, which cancels with our positive 3x, and our positive x squared canceling with our negative x squared. So this actually becomes the limit as delta x goes to 0 to delta x plus delta x squared minus 3 delta x all over delta x. Then we can factor out a delta x. You should be able to factor out a delta x in every limit definition of a derivative you do. We have delta x times 2 plus delta x minus, let's see, did I misplace an x somewhere? 2 plus delta x, let's see. I believe I did actually. This should be a 2x delta x, that's why. That should be a 2x delta x because we would have our x here multiplied by our delta x and then twice. So we have 2x plus delta x minus 3 all over delta x. There we could cancel out our delta x's. So you'd have the limit as delta x goes to 0 of 2x plus delta x minus 3. And then, of course, if you let delta x equals 0, this simply becomes 2x minus 3. So that is our derivative. Make sense? All right, in that case, I'll go ahead and give you guys a couple of practice problems. These are going to be a bit more difficult than this example. So if you have any questions, just go ahead and ask. F of x is equal to minus 2 for x plus 1 squared. And then problem 2 is going to be actually, we'll just have you work through problem 1 for time's sake. All right, so go ahead and try this practice problem out. And just tell me when you're ready. All right. This one was pretty tricky because it just takes a lot of algebra essentially. Like the right path is pretty long and extensive. Would you like me to just go over the answer right now? Because it is trickier. All right. So to start off with, we start by writing our whole equation, which is going to be a limit statement. So first off, the limit as delta x goes to 0 of, we're going to have -2 divided by x plus delta x plus 1 squared, and then minus -2, so just plus 2 over x plus 1 squared. And all of that is going to be over delta x. So if we wanted to make this numerator one fraction, what we can do is we can essentially cross multiply. So the limit as delta x goes to 0, -2 times x plus 1 squared plus 2 times x plus delta x plus 1 squared, all over then the product of these two denominators, x plus delta x plus 1 squared times x plus 1 squared. Then all of that would be over delta x, but since it's just a second denominator, we can just multiply this delta x right there. So if we wanted to continue solving this, that would be limit as delta x goes to 0 of, now we have, if we distribute, we have -2x squared minus 4x minus 2, then plus, let's see, we have to simplify, x plus x plus 1 squared, which I did this before, so I'm just going to say that's x squared plus 2x delta x plus delta x squared plus 2x plus 2 delta x plus 1. So then we would have to, we have to add twice this. So plus 2x squared. And actually, I'm going to reorder this. I'm going to write all of the x squared terms first. All of the terms with no delta x in them first, just so you can see. So we have the x squared, we already did that one, plus 4x, then plus 2. And next we would have plus 4x delta x plus 2 delta x squared, and then plus 4 delta x. And what you'll notice is we actually have a -2x squared here and a positive 2x squared here. So those will cancel. -4x here and a positive 4x here. So those will cancel. And -2 here and a positive 2 here, that also cancel. And of course, this is all going to be over our same denominator, x plus delta x plus 1 squared times x plus 1 squared times delta x. But then you'll notice, since we only have terms with a delta x in the numerator, we can actually go ahead and factor out a delta x. So then we have the limit as delta x goes to 0 of delta x times 4x 2 delta x plus 4. And all that's going to be over our same denominator, x plus delta x plus 1 squared times x plus 1 squared times delta x. And again, our delta x's will cancel on top and bottom. So then we have the limit as delta x goes to 0 of 4x plus 2 delta x plus 4 over x plus delta x plus 1 squared times x plus 1 squared. And because this delta x is simply being added, we can actually go ahead and plug in 0 for delta x to evaluate our limit. So we get 4x plus 2 times 0, so plus 0, then plus 4, divided by, we have, let's see, here we have x plus, sorry, here we have delta x plus 0 plus 1 squared, so x plus 1 squared times x plus 1 squared, which is x plus 1 to the 4th. And that should be our correct derivative. Any questions? Does that all make sense to everyone? All right, cool. So basically, the big things to watch out for with these, using the definition of a derivative to find the derivative, is mostly you do want to simplify everything in the numerator into one term, even if it is something huge, long, and messy, like we did up here. We got all this, but you should always be able to factor out a delta x on top like we did here, and that'll then cancel out with the delta x on the bottom. And after that, you should be able to just evaluate your limit by plugging in 0 for delta x. So sometimes it is a bit difficult to actually see all of this and where you're supposed to be going, but as long as you just look for where you can factor out the delta x, you should be able to figure it out. So let's see. Okay. One thing to note is if you have a sharp term, so for instance, like in an absolute value function like this, where it makes a sharp point, the derivative here actually does not exist. Because if you think about it, you'd have the limit as delta x goes to 0. Well, the slope on this left-hand side is going to be negative. So the limit as delta x approaches 0 from a negative side would be smaller than 0. But from this positive side, you're going to have a positive slope. So this limit of delta x approaches 0 would actually be bigger than 0 and positive. So because these two would actually approach two different values, the actual limit does not exist. So you can't actually take the derivative of a function at a sharp turn like this, such as an absolute value. It can be a very sharp curve. This is still fine. You can still take the derivative here. But a sharp turn, like an absolute value, no. So we'll actually go ahead and move on to a few differentiation rules in these last few minutes. Because luckily for us, we don't actually have to go through that whole definition of a derivative process every time you want to take a derivative. So go ahead and start with something that's called the power rule. And most of you should have heard of this by now. But essentially it says that the derivative of some variable x to the nth power is just n times x to the n minus 1. Bring down the power as a coefficient and then decrease the power by 1. And for those of you who don't know, this d over dx here that I used, that's a way to say that you're taking the derivative. There's actually a lot of different ways we can say that it's a derivative. For instance, we can say dy over dx, and this says the rate of change of y over the rate of change of x. We can say y prime. We can say f prime of x, and there's probably a few other notations that you might come across, but you should usually be able to figure it out that it's a derivative. This is the power rule. So for instance, if we had 4x to the 3/2 and we wanted to take the derivative, well, our power rule says we can just bring down our coefficient and multiply it, so we would have 4 times 3/2. Then we would decrease our power by 1. So 3/2 minus 1 is 1/2. And then if we simplify, we would get 4 times 3 is 12, divided by 2 is 6, x to the 1/2. So why don't you guys go ahead and try out, for instance, 6 over x squared, and also 2x to the 4th. All right, any ideas, anyone? One is negative 12x to the minus 3. Good, good. Again, we can rewrite this 6 over x squared as 6x to the minus 2. So then we multiply by our power. So we get negative 12, then decrease the power by 1. All right, what about number 2? 8x cubed. Good job. We just have 4 times 2 is 8, then decrease the power by 1. That is the power rule. So if we want to, there are some other rules we can use though. The sum and difference rules, basically all those say if we have two functions, f of x plus g of x, then that's just the derivative of the first plus the derivative of the second. G prime of x. So for example, if we had 3x squared plus 3x, then we would just take the derivative of the first, so 6x plus the derivative of the second, using the power rule on both, plus 3. That's easy enough. And we also have a few derivatives of trigonometric functions. So the derivative of sine of x is equal to cosine of x. In fact, if we wanted to say that u was a function of x, so what this says is if we have some function of x inside of our sine, so for instance, if we had sine of 3x squared, then our derivative is just going to be the cosine of that same inside, so cosine 3x squared times the derivative of whatever's inside. So in this case, the derivative of 3x squared is 6x. And for cosine, I'm going to again put it in the form of this u cosine of u is equal to negative sine of u times u prime. And lastly, the derivative of tangent is equal to secant squared of u times u prime. And there are, of course, three other trig functions. You've got cosecant, secant, and cotangent. And you can look up their their derivatives. You can just find those online. But they essentially follow the same pattern as this one. For instance, the derivative of cosecant, which is 1 over cosine, is just going to be secant of u times u prime. The derivative of secant should be cosecant, that is cosecant of u times u prime. And then the derivative of cotangent is actually going to be cosecant, not cosecant. Oh my goodness. It would be, I believe, cosine squared of u. Let me double check that really quick. Sorry, that would actually be, I was right, it was negative cosecant squared. Just a sec. That should be negative cosecant squared for the derivative of tangent, cotangent. But essentially, remember these are all identities, and they are important for you to remember. But they're fairly straightforward. Essentially, sine just goes to cosine, cosine goes to negative sine, tangent being weird just goes to secant squared. And there is actually one other important thing you should know. Applications of derivatives. Velocity is equivalent to the derivative of acceleration. And acceleration is equal to the derivative of velocity. Sorry, velocity is the derivative of position. Just looking ahead in my notes. So, for instance, if you have a velocity function, that's 2t plus 3, and let's say we wanted to find the acceleration at time t equals 4, all we would have to do is say the derivative of our velocity function is going to be the derivative of any constant is 0. So the derivative of 3 is just 0. One way to think about that is if we graphed just 3, it has a 0 slope. So since the derivative is just slope and it has a 0 slope, the derivative is 0. Thus, our acceleration is just going to be 2. Make sense? All right. So that actually does bring us to the end of our time. I'm going to go ahead and